Welcome everyone. Today we are looking at topic 8 in your SS3 physics series, semiconductors. This topic covers semiconductor materials, diodes, transistors, and their applications. This topic is common in essay questions. You must understand the principles and the devices. Pay close attention. Let us begin. First, let me explain what semiconductors are. Semiconductors are materials that have electrical conductivity between that of conductors and insulators. They are the foundation of modern electronics. Silicon and germanium are the most common semiconductor materials. They have 4 valence electrons. This allows them to form covalent bonds with neighboring atoms. At low temperatures, they behave like insulators. At higher temperatures, they behave like conductors. Their conductivity can be controlled by adding impurities. This process is called doping. Understanding semiconductors is essential for understanding electronic devices. This is the foundation of modern technology. Now let me explain intrinsic and extrinsic semiconductors. An intrinsic semiconductor is a pure semiconductor. It has no impurities. Its conductivity is low. It is determined by the thermal generation of electron-hole pairs. An electron-hole pair is created when an electron gains enough energy to break its covalent bond. The electron moves to the conduction band. The hole remains in the valence band. Both the electron and the hole contribute to conductivity. An extrinsic semiconductor is a doped semiconductor. Impurities have been added to increase conductivity. There are 2 types of extrinsic semiconductors, N-type and P-type. Understanding intrinsic and extrinsic semiconductors is essential for understanding semiconductor devices. This is a key concept. Now, let me explain doping. Doping is the process of adding impurities to a semiconductor to increase its conductivity. The impurities are called dopants. There are 2 types of dopants. Pentavalent dopants have 5 valence electrons. They donate electrons to the semiconductor. They are called donor impurities. Examples include phosphorus, arsenic, and antimony. Trivalent dopants have 3 valence electrons. They accept electrons from the semiconductor. They are called acceptor impurities. Examples include boron, aluminum, and gallium. Doping creates either N-type or P-type semiconductors. Understanding doping is essential for understanding how semiconductors are made. This is a fundamental process. Now let me explain N-type semiconductors. An N-type semiconductor is formed by doping a pure semiconductor with a pentavalent dopant. The dopant atoms have 5 valence electrons. 4 electrons form covalent bonds with the semiconductor atoms. The 5th electron is loosely bound. It becomes a free electron. This free electron can conduct electricity. The N-type semiconductor has many free electrons. These are the majority charge carriers. It also has a few holes. These are the minority charge carriers. The conductivity of an N-type semiconductor is high. The Fermi level is close to the conduction band. Understanding N-type semiconductors is essential for understanding electronic devices. This is a key concept. Now, let me explain P-type semiconductors. A P-type semiconductor is formed by doping a pure semiconductor with a trivalent dopant. The dopant atoms have 3 valence electrons. They form 3 covalent bonds with the semiconductor atoms. There is a missing bond. This creates a hole. The hole can accept an electron. The P-type semiconductor has many holes. These are the majority charge carriers. It also has a few free electrons. These are the minority charge carriers. The conductivity of a P-type semiconductor is high. The Fermi level is close to the valence band. Understanding P-type semiconductors is essential for understanding electronic devices. This is a key concept. Now let me explain the p-n junction. A p-n junction is formed when an N-type semiconductor and a P-type semiconductor are joined together. The junction is the boundary between the 2 materials. At the junction, electrons from the N side diffuse into the P side. Holes from the P side diffuse into the N side. This diffusion creates a depletion region. The The depletion region is depleted of free charge carriers. It has an electric field. This electric field prevents further diffusion. The junction has a built-in potential. This is about 0.7 volts for silicon. The PN junction is the basis for many semiconductor devices. Understanding the PN junction is essential for understanding diodes and transistors. This is a fundamental concept. Now, let me explain the diode. A diode is a semiconductor device that allows current to flow in only one direction. It consists of a PN junction. It has two terminals. The anode is the P side. The cathode is the N side. When the diode is forward biased, the positive terminal of the battery is connected to the anode. The negative terminal is connected to the cathode. The depletion region narrows. Current flows easily. When the diode is reverse biased, the positive terminal of the battery is connected to the cathode. The negative terminal is connected to the anode. The depletion region widens. Current does not flow. The diode acts as a one-way valve. Understanding diodes is essential for understanding rectification. This is a key concept. Now let me explain the characteristics of a diode. The current voltage characteristic of a diode shows how the current changes with voltage. In the forward bias region, the current increases exponentially with voltage. The diode starts conducting at a threshold voltage. This is about 0.7 volts for silicon. It is about 0.3 volts for germanium. In the reverse bias region, the current is very small. It is called the leakage current. It is in the microampere range. If the reverse voltage is too high, the diode breaks down. This is called the breakdown voltage. The diode can be damaged if the breakdown voltage is exceeded. Zener diodes are designed to operate in the breakdown region. Understanding the characteristics of a diode is essential for using diodes in circuits. This is frequently tested. Now, let me explain the applications of diodes. Diodes have many applications. The most common application is rectification. A rectifier converts alternating current to direct current. A half-wave rectifier uses one diode. It allows current to flow in only one half of the cycle. A full-wave rectifier uses 4 diodes. It allows current to flow in both halves of the cycle. Diodes are also used in clipping circuits. They limit the voltage. They are used in clamping circuits. They shift the voltage level. They are used in voltage multipliers. They increase the voltage. They are used in signal detection. They extract information from signals. Diodes are used in solar cells. They convert light into electricity. Understanding the applications of diodes is essential for understanding electronic circuits. This is a key topic. Now, let me explain the Zener diode. A Zener diode is a special type of diode. It is designed to operate in the reverse breakdown region. It has a well-defined breakdown voltage. This is called the Zener voltage. When the reverse voltage is below the Zener voltage, the diode does not conduct. When the reverse voltage reaches the Zener voltage, the diode starts conducting. The voltage across the diode remains constant. This property makes Zener diodes useful for voltage regulation. They maintain a constant output voltage. They are used in power supplies. They protect circuits from voltage surges. Understanding Zener diodes is essential for understanding voltage regulation. This is a key application. Now let me explain the LED. The LED is a light-emitting diode. It emits light when it is forward biased. The light is emitted when electrons recombine with holes. The color of the light depends on the semiconductor material. Gallium arsenide produces infrared light. Gallium arsenide phosphide produces red light. Gallium phosphide produces green light. Gallium nitride produces blue light. LEDs are used in displays, indicators, and lighting. They are energy efficient. They have a long lifetime. They are used in traffic lights, television screens, and flashlights. Understanding LEDs is essential for understanding modern lighting and displays. This is a common application. Now, let me explain the transistor. A transistor is a semiconductor device that amplifies or switches electronic signals. It is a 3-terminal device. It consists of 2 PN junctions. There are two main types of transistors: bipolar junction transistors and field effect transistors. The bipolar junction transistor has three regions: the emitter, the base, and the collector. There are two types of bipolar junction transistors: NPN and PNP. The transistor is a fundamental building block of modern electronics. Understanding transistors is essential for understanding amplification and switching. This is a key concept. Now let me explain the NPN transistor. The NPN transistor consists of two N-type regions and one P-type region. The emitter is N-type. The base is P-type. The collector is N-type. The base is very thin and lightly doped. The emitter is heavily doped. The collector is moderately doped. When the base emitter junction is forward biased, electrons flow from the emitter to the base. Most of the electrons pass through the base to the collector. A small current in the base controls a large current in the collector. This is the amplification action. The NPN transistor is the most common type. Understanding the NPN transistor is essential for understanding transistor circuits. This is frequently tested. Now let me explain the PNP transistor. The PNP transistor consists of two P-type regions and one N-type region. The emitter is P-type. The base is N-type. The collector is P-type. The base is very thin and lightly doped. The emitter is heavily doped. The collector is moderately doped. When the base emitter junction is forward biased, holes flow from the emitter to the base. Most of the holes pass through the base to the collector. A small current in the base controls a large current in the collector. The PNP transistor is less common than the NPN transistor. Understanding the PNP transistor is essential for understanding transistor circuits. This is a key concept. Now let me explain the operation of a transistor as an amplifier. A transistor amplifies current and voltage. A small input current at the base produces a large output current at the collector. This is the current gain. The transistor can also amplify voltage. This is the voltage gain. The transistor can amplify power. This is the power gain. The amplification is due to the transistor's ability to control a large current with a small current. The transistor is biased in the active region. This means the base emitter junction is forward biased and the base collector junction is reverse biased. Understanding transistor amplification is essential for understanding electronic circuits. This is a key application. Now, let me explain the operation of a transistor as a switch. A transistor can also act as a switch. When the base current is zero, the transistor is off. No current flows through the collector. This is like an open switch. When the base current is sufficient, the transistor is on. Current flows through the collector. This is like a closed switch. The transistor switches between the off state and the on state. This is used in digital circuits. The transistor is biased in the cutoff region or the saturation region. Understanding transistor switching is essential for understanding digital electronics. This is a key application. Now let me explain the applications of transistors. Transistors have countless applications. In amplifiers, transistors are used to amplify signals. They are used in audio amplifiers, radio amplifiers, and operational amplifiers. In switching, transistors are used to turn circuits on and off. They are used in computer processors and memory. In power supplies, transistors are used for regulation. In oscillators, transistors are used to generate signals. In communication, transistors are used in transmitters and receivers. In sensors, transistors are used to detect light, temperature, and other parameters. Understanding the applications of transistors is essential for understanding modern electronics. Transistors are the foundation of the digital age. Now let me explain the importance of semiconductors. Semiconductors are important for several reasons. First, they are the foundation of modern electronics. All electronic devices use semiconductors. Second, they are used in computers, phones, and televisions. They are essential for communication. Third, they are used in energy systems. Solar cells use semiconductors. Fourth, they are used in medical devices. Pacemakers and imaging devices use semiconductors. Fifth, they are used in transportation. Cars and airplanes use semiconductors. Sixth, they are used in industrial control. Semiconductors are everywhere. Understanding semiconductors is essential for understanding modern technology. They are fundamental to our world. This is topic 8 in your SS3 physics series. Study it well. It is common in essay questions. Well done.